Okay, in the last video we looked at geometric sequences. Now we're going to look at geometric series. Essentially, adding up the terms of the geometric sequence. As far as it goes, there's actually two different cases we're going to look at. There are finite geometric series, and then there are infinite ones. We're going to start with the finite, and then we'll jump to the infinite. In order to find the sum of any geometric series, well, we're going to need a formula, just like we did for arithmetic series. And we can generate it algebraically in the same way, more or less, that we did with the arithmetic ones, just with a different algebraic trick. So for the sake of argument, we'll use s sub n, my nth partial sum, just like we used to. And what is that equal to? Well, it's the sum of the first n terms of the sequence. So that's, let's see, a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus all the way out to a sub 1 times r to the n minus 1. That's the first n terms of my geometric sequence. Add them all up and I get s sub n. And now when we were trying to prove the arithmetic series formula, we did a little algebraic trick where we combined two series. We're going to do something similar to that here. First, I'm actually going to take this series and I'm going to multiply the whole thing by r on both sides of the equation. So I'll get r s sub n equals, and now just multiply each term by r. So we'll get a sub 1r plus a sub 1r squared plus a sub 1r cubed plus all the way out to a sub 1r to the n. Well, okay, that's a neat little trick. Now, what can we do with it? Well, last time for the arithmetic sequences in series, we added those two series together and then did something algebraically from there. Here we're going to do something slightly different. We're going to subtract those two. If you subtract them, on the left, you'll get s sub n minus r s sub n. On the right, well, let's see, here's an a sub 1, but then if we look at it, this is a sub 1 times r, there's an a sub 1 times r right there. So when I subtract these, those two terms will cancel. But then there's an a sub 1r squared, there's an a sub 1r squared. So when I subtract, those two will cancel. This kind of diagonal approach will continue. This a sub 1r to the n minus 1, there'll be one of those terms right here. And then the only term actually left over will be this last term right here, because there's no r sub n term up here. Keep in mind we're subtracting them, so when we subtract, that actually becomes negative, and it becomes minus a sub 1 r to the n. But now we have a nice simple formula right there. Factor it on both sides. On the left, there's a common s sub n, so if we factor it out, we're left with 1 minus r. On the right, there's a common a sub 1. Factor it out, and you're left with 1 minus r to the n. And now our ultimate goal was to solve for s sub n, so divide by 1 minus r. And we get s sub n equals a sub 1, 1 minus r to the n, over 1 minus r. And there we go. There's a nice formula for the sum of the first n terms of a geometric sequence. Well, now I suppose we can at least use it to see how it works. So let's see, we'll rewrite the formula just so we keep it in mind. S sub n equals a sub 1 times 1 minus r over n over 1 minus r. So just to see it in practice how it works, suppose I know that a sub 1 equals 2 and r is equal to, we'll make it fun, we'll say 3. I want to find s sub 10, the sum of the first 10 terms. Actually, we'll make this a little bit smaller. We'll say s sub 6. Well, by definition, what is s sub 6? It's a sub 1, 2, times 1 minus r to the n the ratio is 3, and n is 6, so that's 1 minus 3 to the 6, all over 1 minus r, which is 3. Well, let's see. That's 2 times 1 minus 3 to the 6th. Let's see. 3 to the 6th, 3 squared is 9, which means we really just have 3 squared. You guys can put this in your calculator. 9 times 9 times 9 is 729. So that's 1 minus 729. All over 1 minus 3, which is negative 2. But now, the 2's here will cancel, the negative will carry along, and it's negative times 1 minus 729, which is negative 728. 2 negatives cancel, and we get 728. And there we go. Nice and simple, good to go. These can get messier. Again, like I had said earlier, if your ratio is a fraction, and then it just comes down to making sure you put it in your calculator correctly. So, really quickly, suppose a sub 1 equals 1, and r is equal to 1/2. We'll just do s sub 5. By definition, s sub 5 is a sub 1, 1, times 1 minus 1/2 to the 5, all over 1 minus 1/2. You can just throw all that into your calculator. The tendency when people are putting it in their calculator is to put it in wrong and get the wrong answer. So if you're going to use your calculator, just make sure you do it carefully. If we actually write this out, the 1 here doesn't matter because we're multiplying. We get 1 minus 1/2 to the 5th is 1 over 32. All over 1 minus 1/2, which is 1/2. 1 minus 1 over 32 is 31 over 32, all over 1 over 2. Now just do the whole division, keep, change, flip thing. The 2 comes up top, 32 goes on the bottom. We get 62 over 32, which is equal to 31 over 16, which is 1 and 15/16. If you want an actual decimal answer, you can throw it into your calculator. I think you get 1.9375, right around there. Just throw it into your calculator and get the answer if you care about that. But again, as long as you know the formula, principle is pretty easy. Find a sub 1, which you probably already know. Use your ratio, plug in n, hit enter on your calculator, and you're done. Just be careful when you do it. So that's the sum of a finite geometric series. But the question becomes, can you find the sum of an infinite geometric series? Well, if you think about it, if my ratio is like 2, then no matter what number I start with, whatever a sub 1 is, we'll pick a really small one. We'll say a sub 1 equals 1. Suppose the ratio is 2. Well then, a sub 2 would be 2, a sub 3 would be 4, and it would keep on going. The a's would get bigger and bigger and bigger, and if I add them all together, well, I'm just going to get infinity, because they keep getting bigger. Maybe if I do the same thing, but I change my ratio, and I make it 1. Well, if I make it 1, then a sub 1 is 1, a sub 2 is 1, a sub 3 is 1, and so on. And I add the number 1 an infinite number of times. And that's still just going to be an infinite number of 1s, which is going to give me infinity. Which means to a certain extent, well, if the sum is infinity, then what does it really matter? But as it turns out, what happens if my ratio is less than 1? Can I do something with that? And essentially, this is kind of an algebraic idea that we can kind of see here. So suppose we have this s sub n, and I'm just going to write s sub infinity right there, meaning the infinite series, the sum of an infinite number of terms. Well, then that should be equal to a sub 1 times 1 minus r to the infinity. Again, we can't do r to the infinity. I'm just using that for a symbol's sake. All over 1 minus r. But now think about it. suppose my ratio is less than 1. Suppose for the sake of argument my ratio is a half. Well, if the ratio is a half, when I take that ratio and raise it to infinity, again, I can't really do that, it's a principle. If I raise that ratio to infinity, what happens? Well, r squared is a fourth, r cubed is an eighth, if we jump around, r to the fifth is 1/32, r to the 10th is 1 over 1024. And clearly, the bigger n gets, the smaller the ratio gets, which makes sense, we're raising a ratio and multiplying it by itself. And as the power gets really, really big, this fraction will get really, really small. Which means in mathematical terms, this thing will approach 0. And essentially, we'll be subtracting 0. Because these things are just going to get smaller and smaller and smaller, which will make them approach 0. Which means, in my formula here, r sub infinity will actually just become 0. But that means, well, if that's 0, then to find this infinite sum, again, we'll just call it s sub infinity, that's a sub 1 times 1 minus 0, which is just 1, so that doesn't matter, all over 1 minus r. And as it turns out, that's actually the formula for the sum of an infinite geometric series as long as the absolute value of r is less than 1. That's a nice, simple, easy formula to work with. We actually kind of have already seen it. The last one I think we just did was we found, let's see, that if we had r equal to 1, a sub 1 was equal to 1, and r was equal to a half. We found s sub 6, I do believe. And when we found s sub 6, I think it was s sub 5. When we found s sub 5, we solved it all out, and we got 1.9375. Well, now suppose I say, well, that's s sub 5. What if I wanted to find s sub 10, or s sub 20, or s sub infinity? Well, according to the formula I just did, s sub infinity is a sub 1 all over 1 minus r, which is 1 all over 1 minus a half, which is 1 over 1 half, which is 2. And what does that really mean? Well, essentially, there's an idea going on here. If I start at 1, well, let's see. S sub 1 would just be 1, the sum of the first term. S sub 2 would be the sum of the first two terms. Let's see, if my first term is 1, I multiply by a half, the next term is a half, that would be 1 and a half, 1.5. If a sub 1 is 1, a sub 2 is a half, a sub 3 is a fourth, well then s sub 3 would be a half plus a fourth plus 1, 1.75. And we can keep on doing this. We already saw this one right here. And yet what this is telling me is no matter how far along I go in my sequence, I'm never actually going to pass 2. Even though at s sub 3 I'm already at 1.75, which makes sense if you think about it, because I'm going to keep on adding on smaller and smaller and smaller and smaller increments, which means, yes, this will keep getting bigger, but it'll get bigger by smaller and smaller and smaller and smaller amounts, and we'll actually close in on the number 2 right here. I'm aware this idea is a little bit confusing if you haven't seen it before, so ponder it and think about it. Mathematically, it's really interesting and something we want to be able to work with.